就是因为你每次都不来，你知道吗？你每次都最后一个来，这样你会有没来，他就预定那个位置。
Okay, guys, we're gonna start. So I'm gonna give the first half of this recitation. It's going to be a linear algebra review, and then Sherry is going to give the second part, which is about optimization. So we're going to go over some linear algebra concepts that are important for the course. So we're going to cover metrics, vector spaces, Banach and Hilbert spaces, and matrices, other like concepts related to matrices that you must have seen before in other courses. Okay, so first, what is a metric? So given a space X, then a metric is a function that takes between two elements of that set that maps into R0 plus, into positive real numbers. So if such a function is a metric if it satisfies those following properties. So d of xy is equal to 0 only if and only if x is equal to y. D of xy is equal to d of yx. And finally, d of xy is smaller or equal than the sum of d of xz plus d of zy. Okay, and this is what you might know as the triangle inequality. So let me give you an example so you can understand more. An example of a Euclidean of a metric, which is a Euclidean distance. So so given the space X, which is Rn, and given two vectors in that space, then the Euclidean distance is, you're familiar with that, it's the sum of the squared elements of the square of each element to the root of that entire sum. And so we can check that for the Euclidean distance, d if between 2 points A and B is 0 if the 2 points are equal, so if A equals to B. And also, the distance between A and B is equal to the distance between B and A. And finally, the distance between A and B is smaller or equal to the distance between A and C plus the distance between C and B, which is a triangle inequality. Okay? So vector spaces. So a vector space is a space X in which, for any two elements, X and Y, in that space, we have the following, and for any alpha in R, we have those following properties. X plus Y is also in the space X. It also belongs to the space X, and alpha X is also in the space X. So as an example, real numbers constitute vector spaces. So if you have two real numbers, X and Y, the sum X plus Y is also a real number. And also, alpha X is also a real number. Another example of a vector space is Rn. So you might have used that in 2D, for example, two vectors in 2D, X and Y. The sum of X plus Y is also in R2, if we're talking about R2. And also, alpha X is in R2. Another example of a vector space is a space of polynomials of size n. Okay, so if we're given two polynomials of size n, like for example here, f of x sorry, polynomials of order n, like f of x and g of x here. F of x, you know how to write a polynomial. It's the sum of ai xi, and g of x is the sum of bi xi. So the summation of those two polynomials is also a polynomial because every order x gets the addition of the two coefficients from each polynomial, and so it is a polynomial of order n. And alpha f of x is also a polynomial because we just scale every ai by alpha. So the set of polynomials of order n is also a vector space. Now we're going to get to the concept of a Cauchy series. So in a given space X, a Cauchy series is a series Xi for which that converges. So in mathematical terms, for every epsilon larger than 0, we can find an n0 such as for all of the m and n in this. So for all of the later terms in the series that are larger than n0 or after n0, the distance between those two terms is smaller than epsilon. So in other terms, the series is converging to a certain number. This is what a Cauchy series is. And so a complete set is a set in which that contains the limits of all of its Cauchy series. So for example, if you think of the set 0, 1, and of the series 1 over n, for n greater than 1. So so the series of 1 over n is all included in the space from 0 to 1. But if we take the space from 0 to 1 without 0 and 1, so the segment excluding the 0 and 1, then this is not a complete set because the limit, which is 0, the limit of 1 over x, is not in the set. Again, we can construct a set in the set of rational numbers. We can construct a series of numbers that converges to square root of 2. But square root of 2 is not a rational number, so the set is not of Q of rational numbers is not complete. But a set of real numbers, for example, is complete. So, okay, now norms. So given a vector space, a norm is a mapping from that vector space to R0 plus, and it satisfies the following properties for x and y in the vector space. So the norm of x is 0 if and only if x is 0. The norm of alpha x is the absolute value of x times the norm of x. Sorry, the absolute value of alpha times the norm of x. And finally, the norm of x plus y is smaller or equal to the norm of x plus the norm of y. And this is the triangle inequality. Also, a norm can instantiate a metric if we write, so the norm of x minus y follows all the rules of a metric and is actually a special case of a metric. Okay, so now we come to the definition of Banach spaces. So Banach spaces is a complete vector set that also has a norm. For example, LPM spaces. So this is these are defined on the set. So these are vector spaces of the type R to the m. So for example, R2 or R3 or R4 with a norm, with a p norm. A p norm is similar to L1. You might have seen L1 or L2 or L3. A p norm is the sum from 1 to the number of dimension of each element of the vector to the power p, and all of the sum is to the 1 over p. Okay. So we have LP spaces too. LP spaces are in a space that is in Rn and being infinite. So they're not finite dimensional vectors. And so this is shown here in this part of the summation where you go from 1 to infinity. So so these spaces are not complete for any measure. For example, if you think of the Cauchy series 1 over x, 1 over I, then this is complete. This is complete if you use L2, but it is not complete if you use L1 because the summation is not going to converge. Okay. And finally, you can also have function spaces. So instead of a summation, we're going to use an integral over a certain function, and also with a given LP. And of course, not all functions are going to be complete, to have a complete representation over every norm. Hilbert spaces. Hilbert spaces is a bit similar. It's a complete vector space that has a dot. Sorry. So before we go talk about that, so dot products first. So a dot product, I'm sure you've seen it before in calculus. A dot or linear algebra. So a dot product is a function that goes from two elements of x into R, and it satisfies the following properties. So there's a symmetry. The dot product between x and y is equal to the dot product between y and x. Linearity. So the dot product between x and alpha y is equal to alpha times the dot product of x and y. And additivity. So the dot product of x and y plus z is the sum of the dot product of x and y and x and z. So finally, Hilbert spaces. So a Hilbert space is a complete vector space with a dot product. And so the dot product can be used to generate a norm because it's just the norm of x is actually the square root of the dot product of x with itself. And so Hilbert spaces are a special case of Banach spaces. So an example of Hilbert space is a Euclidean space with the standard dot product for x and y in Rm. We can also have function spaces. So if you think of functions that map from x to the complex to the set of complex numbers, then we compute the dot product by replacing the sum with an integral like before, and it's the integral of the complex of x times g of x. And so this is how you can compute dot products for functions. And finally, we can have L2 series of real numbers, or LP series of L2 series of real numbers in the same way. So we don't have to stop at m. We can have infinite dimensional dot products. Okay. So matrices. So we can think of a matrix as a map from a space in Rm to a space in Rn, because that's what you do when you multiply something by a matrix. And so a symmetric matrix in a symmetric matrix is a matrix that is square first. It's in Rm times m, and it satisfies the property that m of ij is equal to m of ji. An anti-symmetric matrix satisfies the property that m of ij equals minus m of ji. And finally, you should have seen before the notion of rank. If you think about it, a rank, if you think of the image of Rm under the matrix M, and you call it I, then Rm is the rank of M is the smallest number of vectors that span that image I. Or if you think about the eigenvector decomposition or eigenvalue decomposition of a matrix, then the rank of the matrix would be the number of non-zero eigenvalues you have. So there's an important concept with matrices is orthogonality. And so a matrix M is orthogonal if M transpose times M is equal to I, which is the identity matrix. So this means that so the M transpose is equal to the inverse of M. Okay? And orthogonal matrix consists of mutually orthogonal rows and columns. So if you do their dot products, you're going to get 0. We're going to introduce now the concept of matrix norms. The norm of a linear operator between two Banach spaces A and X, so the norm of a matrix, as we said before, is the norm of a matrix A is the maximum over all the x's in the set of this term, which is ax, the norm of ax divided by the norm of x. Okay, and so this terminology applies. So this definition follows the 3 rules for having a norm. The first one is that the norm of ax is going to be the maximum over all x of alpha ax over x, and so it's going to be equal to alpha, the absolute value of alpha times the norm of A. Okay. And the second requirement for a norm is that the norm of A of B is the triangle inequality, right? So the norm of A plus B is going to be equal to the maximum of A plus B times x over x. And this is smaller or equal to the maximum of the norm of AX over x plus the maximum of norm of BX over x. And so this is equal to the norm of A plus norm of B. And so we get the previous inequality, which is that norm of A plus B is smaller than norm of A plus norm of B. Okay? And finally, norm of A equals 0 means that since norm of A equals 0 means that it means that the maximum of this expression is supposed to be 0 for all x, and so ax equals 0 for all x, and so A is equal to 0.
Excuse me, can you give me an example about the definition of this, like how to calculate matrix norm?
An example of a matrix norm?
Yeah, I'm just wondering why it is a maximum of ax over ax norm over x norm, and are there more than one values here?
Yeah, because well, the value of the way the matrix is going to shape the vector x, it depends on the value of the input x.
I mean, can you give like 2 by 2 matrix an example?
I'm sorry, I can't hear you.
Can you give a 2 by 2 matrix as an example?
Yeah, sure.
Thanks.
So one way, maybe it's better to So what we want to do is we want to know how much, like what's the effect of this matrix on transforming a vector x, right? So we want to maximize the output, which is ax. We want to maximize this norm divided by how big x is, right? Because then you're gonna multiply this by x. Exactly.
Oh, so x is a vector.
Yeah, x is a
one
vector.
column vector.
Yeah. X is going to be 1%. But so the value of x is you want a measure of the matrix that is not dependent on how big the value of x is.
So maybe the product of these two is a row vector, and it will calculate the maximum entry in that row vector, right? The column vector.
It's going to get more clear as we go through this. Let me continue because I still have only 12 minutes left.
Is that x and y a typo, or is y sign this line? At the very top of the slide, Banach Spaces x and y.
No, it is. No, it is correct. It's x and y. So x is Rm, the first dimension of the matrix, and y is Rn, which is the second dimension of the matrix. So that was one example of a matrix norm. We can have another example of a matrix norm, such as the Frobenius norm. Okay, so this is an analog to how we get a norm for a vector by doing a L2 distance or something. And the Frobenius norm is the summation over all the columns and the rows of the squared value of every term in the matrix. Okay. So now we're going to get to eigensystems. So given a matrix M in R that is symmetric, a square matrix M in R M times M, then lambda is an eigenvalue of M, and X is an eigenvector if we have this equality, which is mx is equal to lambda x. So this is the definition of eigenvalue and eigenvector. So for symmetric matrices, we have a lot of nice properties. The first one is that all the eigenvalues are real, and the matrix is fully diagonalizable. Okay, so we get m eigenvectors. We have that all eigenvectors with different eigenvalues are mutually orthogonal, and we can get that because if we think of if we think of two different eigenvalues and eigenvectors, so lambda and x and lambda prime and x prime, and if we look at this x prime, okay, so this is equal actually to so we said before that an eigenvalue says, sorry, let's see. Right, so this term is going to be equal to m transpose x prime, which is going to be equal to lambda m transpose x. Yeah. So this is equal to x transpose m transpose x. And so this is and this part. So this part is equal to
because the m transpose is m. So that would be lambda prime x prime.
M is symmetric.
sorry?
M is symmetric.
Because m is symmetric, so m transpose is equal to m itself.
Right, yes. I mean, it's right there. Right. Sorry. Okay. So this would be equal to lambda prime x prime. Right. So we have either that lambda is equal to lambda prime, or that the product xt is 0. xtx is 0. Okay, so that's why different eigenvalues are going to have orthogonal eigenvectors. Okay? And we can decompose M into O transpose lambda O. In O, we're going to have mutually orthogonal eigenvectors. In lambda, it's a diagonal matrix with all of the eigenvalues on the diagonal. And so we don't have time, a lot of time left to go into everything else, but I can take questions later on. Sorry for not having time. So for the operator norm with a symmetric matrix, we end up having that the norm of M is actually the maximum eigenvalue squared of that matrix. And also the Frobenius norm ends up being the sum of the squared eigenvalues of that matrix for a symmetric matrix. Okay, so the trace of a matrix is the summation of all of the elements on the diagonal for that matrix. We have the property that trace of AB is equal to the trace of B times A. And for symmetric matrices, the trace of M is going to be the trace of the trace of M is actually going to be the sum of all of the eigenvalues, because if we write M in the orthogonal way we saw before, then since trace of AB is equal to the trace of BA, we can rotate the matrices. And O is an orthogonal matrix, so this is equal to identity, and that's why the trace of a symmetric matrix is a summation of the eigenvalues. And the same for the determinant. We also have that the determinant is the product of all of the eigenvalues. Okay. A positive definite matrix is a matrix for which we have this property. So xt times m, x transpose times m times x is greater than 0 for any x that is not 0. Okay, and so that's why such a matrix only has positive eigenvalues, because we can replace this term here by lambda x transpose, as we were trying to do before, and we obtain lambda times the norm of x. So if x is not 0, then lambda cannot be 0. And finally, we want to use a similar decomposition for arbitrary matrices, not only for symmetric matrices. And so when we do SVD, you're going to see that we can write a matrix M in this fashion, U times lambda times O, in which both U and O will be orthogonal matrices, and lambda will contain all of the eigenvalue for M. But we're actually going to have to look at M transpose M in order to get those values. Yes?
Is it always going to be the eigenvector or not?
U is going to be there.
U? Oh, yeah.
Tomorrow, Alex is going to cover support vector machines. So I hope this recitation will give you some basic ideas about convex optimization. So I'm going to talk about convexity unconstrained convex optimization, including first order and second order methods and constraint optimization. First, convex sets. So a set is defined as convex if you choose 2 points in this set. If you draw a line segment between these 2 points, this line segment is still belongs to this set. The definition is here. So if you imagine this, a circle would be an example of convex set. And other examples include the empty set, a single point, the whole space, and the hyperplane. In two-dimensional space, a hyperplane will just be a straight line. And the half spaces, also in two-dimensional space, a straight line will cut the whole space into 2 half spaces. And the Euclidean walls, and the positive semi-definite matrices. Here are some convexity preserving set operations. So if we have 2 convex sets, C and D, if we do the following operation, we will end up with another convex set. The operation include translation, scaling, affine function, intersection, and set sum. So now I'm going to introduce a convex function. A function is defined as convex if we take 2 points in this function and we draw a line between them. This line segment will lie above the function value between these 2 points. So here is the definition. We have other conditions to check whether this function is convex or not. So the first order condition says that if f is differentiable, then if fy is larger or equal to fx plus the derivative of fx times the difference between y and x, this function will be convex. Geometrically, it means if we have a point x here, and we draw a line starting from x, and the slope is the derivative of fx, then this line will lie below the function. The second order condition says that if f is twice differentiable, then the Hessian matrix will be positive semi-definite. If we change the conditions a little bit, we will end up with a strictly convex function, which means that the Hessian matrix of this function is positive definite. And also we have this strongly convex function, which means the Hessian matrix minus the d times the identity matrix will be positive semi-definite. Here are some properties of the convex function. So first, a below set of a convex function is convex. Here is the proof. A convex function don't have a local minimum. We can easily prove this by contradiction. So imagine if there's a convex function and there are 2 local minima. And if we draw a line between these 2 local minima, the value, this line will lie below the whole function, not the whole function, the function value between these 2 local minima, which is a contradiction to the definition of convex function.
Sorry. So should that be they don't have local maximum?
Local minimum. Yeah. A simple example of convex function would be x squared. X squared is a convex function. So every convex function has a global minimum. So here is another a definition of convex Hall. So a convex Hall is actually the smallest convex set that containing all the points in X. No matter the original set is convex or not, the convex Hall of a set is always convex. So here are some convex function examples. The exponential function is a convex function. The powers of x is convex only if A is larger or equal to 1 or smaller or equal to 0. And this function will be concave if A is in the interval 0 and 1. The powers of the absolute value is a convex function if P is larger or equal to 1. The logarithm function is a concave function. Every norm is a convex function. And the maximum function is also a convex function. And the log sum exp function is also a convex function.
What is the R double plus?
This means the domain of this R is the real value space. Plus plus means it's in the positive part. If there is only one plus, it means non-negative part. So there's 0 and positive. So here are some convexity preserving function operations. If we already have two functions f and g, the non-negative weighted sum of these two functions will be a convex function. The pointwise maximum of convex functions will be convex. The composition with a affine function will also be a convex function. And the composition with non-decreasing convex g, this gfx function is also convex. You can easily check these functions to be convex by using the definition first order or second order conditions. Now I'm going to talk about unconstrained convex optimization. So here, first I'm going to introduce the first order methods. There are a lot of first order methods, but gradient descent is one of them, and it's the simplest one. So the algorithm is shown above. So we are given a starting point x, and we repeat doing this procedure. We compute the derivative of at x, and we take the negative of the derivative. And then we choose a step size by exact or backtracking line search. And then we update this x by x plus the step size times the negative derivative. So the key idea here is the gradient actually points into the descent direction. And locally, the gradient is a good approximation of the objective function. The above algorithm is actually an example of the gradient descent with line search. So how fast does it converge? There are two convergence analyses. So first, if the derivative of f is L Lipschitz, then the gradient descent with a certain step size will have convergence rate O1 over k, which means if we want to get a function value at the kth iteration be epsilon close to the optimal value, then we need O1 over epsilon iterations. So the second one says that if stronger condition holds, if stronger convexity holds for this f function, then with a certain step size, we can get convergence rate OC to the k, which is exponential faster than faster than first one. So Newton's method is a second order method. So we have a convex objective function f. So this function will have a non-negative second derivative, which means the Hilbert matrix will be positive semi-definite. If we do a Taylor expansion on this fx plus delta, and Newton's method tries to minimize this function by finding an appropriate delta. So we just need to take this function and take the derivative with respect to delta. And the solution will give delta equals to the inverse of the Hilbert matrix times the first derivative. So delta is the direction we want to go, which means the update step will be we assign x to be x minus delta. So how fast does Newton's method converge? There are two convergence regimes. In the first regime, Newton's method can be as slow as gradient descent if the Taylor expansion is not good enough. But once the Taylor expansion is good enough, which means this bound holds, then Newton's method will achieve quadratic convergence. So if you look at this, n plus 1 is the x value we are going to choose in the n plus 1 iteration. And xn is the x we choose in the nth iteration. Then x star is the optimal value. The difference between the x value in the n plus 1 iteration and the x star will be it's smaller than the original difference squared. So if we regard this xn minus x star as an error, then the error will be squared, reduced squared. So now I'm going to talk about constraint optimization. So what is constraint optimization? Originally, we have this function, this objective minimize the fx function. But now we have some constraints. So basically, a lot of constraints can be written in this way. So we have some inequality conditions, and we also have some equality conditions. We define the Lagrange of the original primal problem as Lx uv equals to fx plus ui times hix, which is hix is original inequality condition, and ljx is original equality condition. Here ui and vj is called the Lagrange multipliers. We only need to require that u is larger or equal to 0. We have no constraint on the vj. So the Lagrange dual function is defined as we minimize this Lagrange over the whole space. So you may ask why we need to define a Lagrange dual function. So the original primal problem can be written in this way. C is defined as the primal feasible set, which means if x belongs to C, then x satisfies the inequality and equality conditions. So the primal problem can be just rephrased in this way. This one, this formula will be larger than this is true because fx will be larger or equal to the Lagrange since hrx is less or equal to 0 and ljx actually is equal to 0. And if we do a minimization on this Lagrange, it will be larger than here, R we are doing a minimization on over the whole space, it's gonna be smaller than doing a minimization over a constraint space. So this inequality always holds. And now we define this minimization as GUV. So it's like if we have this GUV function, it's always smaller than the original primal function, right? Let me draw a picture here. Suppose the original problem just looks like this way, and we want to find the minimal point here. And this GUV function will always be smaller than that. For example, like this.
Excuse me, but smaller you mean lower dimensions or?
Not lower dimension. The value is always smaller than. So now we have this GUV function. What will we do? The best we can do is to maximize.
Why there is no constraint on V? We are saying that U should be bigger or equal to 0, but there is no constraint on V, yeah?
Yeah, because LG is an equality condition. So we only need this inequality to be held. So as fx is larger than this Lx UV function, if u is larger or equal to 0 and h is smaller than or equal to 0. And because L is always equal to 0, we don't need any else constant on V, right? Okay, so now if we have this GUV function, the best we can do is to maximize this GUV function. And hopefully we can get, if the maximal value is here, hopefully we can get an answer close to the original one, primal problem. Why is this GUV function nice? Because if we look at this, GUV is a minimization over the Lagrange function. And Lagrange function is a linear function in U and in V, U and V. So it is a minimization, it's a pointwise minimization over a linear function in U and V. I should mention that a linear function is always a convex function. So a pointwise minimization over a linear function is actually a concave function. Remember I said before, a pointwise maximum of the convex function is convex. Then the pointwise minimum of convex function is a concave function. So because this GUV is a concave function, this dual problem actually can be, actually is a convex optimization problem. So which makes it much nicer because we can see that GUV has a local maximum, has a global maximum. So the original primal problem will be reduced to just finding the global maxima of the Lagrange function. Here I have written that the primal and dual optimal values always satisfy weak duality, which means the primal optimal value is larger or equal to the dual optimal value. And now you may also ask, this dual optimal value actually is smaller or equal to the original primal optimal value. So how can we guarantee, if we found this value, how can we guarantee it is close to the optimal, the primal optimal one? So here is a nice conclusion. Slater's condition says if the primal is a convex function, and if there is an x which satisfies these, strictly satisfy these inequality conditions and the equality conditions, then strong duality holds. Strong duality holds means that the primal optimal value is equal to the dual optimal value.
So what if the strong condition does not hold? So we don't have such condition, right?
Yeah, we don't have such condition.
So we only know that in a constrained space.
Yeah, we will get a lower bound of the
So just get a lower bound.
Right. Yes. And this is another nice conclusion. It's that it is called KKT conditions. So if X star, U star, and V star are primal and dual solutions, and strong duality holds, then X star, U star, V star will satisfy the following KKT conditions. There are 4 of them. The first is called the stationarity condition, which means if we take derivative with respect to x of the Lagrange function, then x star, if we replace the x star value in this derivative, it will equals to 0, which means x star actually minimizes the Lagrange function. The second one is called complementary slackness, which means for each I, ui times hi equals to 0. This means for each I, either ui equals to 0 or hix equal to 0. The third one and the fourth one is just primal feasibility and the dual feasibility. I provide a proof here. So actually, this is very easy. If you look at this, the first equation holds because the strong duality holds. The second one, GU star V star equals to this, is just the definition of the Lagrange function. And the third inequality holds because if we do a minimization over a function, it will be smaller than the function with any value in it. And the last inequality holds because x star is the primal optimal value, so it's in the primal feasible set. So here, ui star is larger or equal to 0. Hix star is less or equal to 0. And this term equals to 0. So the whole term will be less or equal to fx star. So if we look at the first term and the last term, actually they are the same. So we can say that actually these two inequalities are actually equalities, which means that from this step to this step, x star actually minimizes the above function. And from this step to this step, which means ui star times hix star should be 0, which exactly gives the first two conditions of KKT conditions. If you want to know more details about convex optimization, you can check out this book. Okay, thank you. Do you have any questions?
So what would you prefer to formulate a dual way instead of
Because the dual function is a concave function. Actually, convex optimization is nice because it has a global maximum or minimum.
But what if the primal is already